Today, we're diving into a concept that honestly prevents total chaos every single time you click a button online. It's called idempotency. Think of it as the unsung hero of our digital lives, the thing that stops that feeling of digital déjà vu. And understanding it is absolutely critical if you want to build systems that don't fall apart.
Okay, just imagine this for a second. We've all been there, right? You're buying something online, you hit that pay button, and your internet just glitches. So what do? You click it again, just to be safe. But then, a few minutes later, you check your bank account and boom, you've been charged twice. It is the absolute worst-case scenario, and idempotency is literally the only thing standing between us and that kind of digital nightmare.
Now, in a perfect world, everything just works. It's what we call the happy path. You click the button, the server does its thing, and you get one single successful result. Simple, clean, exactly what we all expect to happen.
But what happens when things aren't perfect? What if that connection drops after the server has already taken your money, but before it can send you that little success message? Well, from your end, it looks like it failed, so you retry. And the server? It has no memory of what just happened, so it happily processes the payment all over again. And just like that, you've got a serious problem.
And here's the wild part. This isn't just some simple bug you can patch. No, this is a fundamental challenge that's baked right into the design of modern distributed systems, where different parts of an app are all running on separate computers. And the real irony, these systems are built this way to be more resilient, but that very design is what creates this exact problem in the first place.
So when you're working with these distributed systems, you have to play by a different set of rules. For one, there's no such thing as a single, clean transaction that touches multiple services. It just doesn't exist. Any single step in the process can fail all on its own. So the core philosophy, the mindset you have to adopt, is to design for failure. You have to assume that things going wrong isn't the exception, it's the normal state of affairs.
You see this all the time with messaging systems like Kafka, which is super popular for moving data between services. See, to make sure a message is never lost, Kafka makes a promise: at least once delivery. What does that mean? It means Kafka would rather send the same message twice than risk it not being delivered at all. The system itself is literally designed to create duplicates. Crazy, right?
So if the very tools we're using are built to create these duplicates, how on earth do we fix this? Well, the answer comes from a really powerful, really elegant computer science principle: idempotency. Okay, let's break that down. In simple terms, an operation is idempotent if you can do it once, or 100 times, or 1,000 times, and the final result is exactly the same as if you'd only done it that first time. It's all about making an action safe to repeat, without any weird side effects. And this is the perfect way to visualize it. Let's say your account balance is $100. If the command is add $5 and you run it twice, well, now you've got 110. That is not idempotent. But if the command is set balance to $105, you can run that once, twice, a dozen times, and your balance will still be 105. That is idempotent. The set operation is safe to retry. The add operation is dangerous. Okay, so the theory is great. It makes perfect sense. But how do you actually, do this in your code? Well, a really common way is to use a special library built just for this, and the one we're going to look at is called ExecutionGuard. And its mission is really simple but incredibly powerful. You basically hand it a chunk of your code along with a unique identifier, like a transaction ID. And what ExecutionGuard does is guarantee that block of code runs at most once for that specific ID. It completely flips that at least once problem on its head and gives you an at most once guarantee instead.
So how does it actually pull this off? Well, when a request comes in, ExecutionGuard first looks in a database for that unique key. If it's never seen it before, it creates a new record and marks it as in progress. Then, and only then, does it run your code. If your code succeeds, fantastic. It updates the record to done and saves the result. If something goes wrong and your code fails, it just deletes that in progress record, so it's safe to try again later.
Okay, and this is where the real magic comes in. What happens on a retry? Well, if that duplicate request comes in and ExecutionGuard sees the status is already done, it doesn't run your code again. Nope. It just grabs the saved result and sends it right back. And if a second request shows up while the first one is still running, while the status is in progress, it just throws an error to stop two things from happening at the same time.
Now, this sounds amazing, and it is, but it's not a silver bullet, and it's definitely not free. Adding this layer of safety comes with a cost. We're talking performance and complexity, so it's really, really important to know when it's the right tool for the job.
The thing to remember is that every single one of these checks means talking to a database. You're doing reads and writes, And that's why, as the library's own documentation puts it, you have to ask yourself, do you really need it? This isn't something you just sprinkle all over your code like magic dust. It's a scalpel meant for very specific, high-stakes operations.
And to put a number on that cost, the source material estimates it's around $4 to $5 for every million requests. Now, look, for a feature that doesn't get much traffic, that's basically nothing. But if you're talking about a core system that handles billions of requests, that cost adds up, and fast. It forces you to make a really critical decision. What's worse, the cost of a duplicate actually happening or the cost of preventing it?
So this really gives you a simple framework for making that choice. Your first option, and probably the default, should be to just accept duplicates if they don't cause any harm. Think about something like a logging service. An extra log line isn't the end of the world. You only bring in a tool like ExecutionGuard when a duplicate would cause real actual damage, like that double charge nightmare we started with. And that third option, relying on another system to be idempotent for you? Yeah, that's pretty rare, so don't count on it.
Okay, so wrapping your code in this library is a fantastic solution. But what if I told you that you could get this exact same protection in some cases with basically zero changes to your code?
Yeah, for certain kinds of services, a developer doesn't have to wrap anything. They can just add this little tag, this annotation, right on top of their function. And just like that, the framework applies all of that ExecutionGuard logic automatically, behind the scenes. It's a beautiful example of a core design principle, making the safe way the easy way.
But it's super important to remember that idempotency, as powerful as it is, isn't a silver bullet. It's just one tool, a really crucial one, in a much bigger toolkit for building systems that can withstand failure. So let's zoom out and see how it fits into that bigger picture.
You'll see it used alongside other smart design patterns. For instance, there's something called the zombie pattern. It sounds cool, and it is. It's where you create something in a safe, pending state first before you commit to the real action. Or another one, async follow-up, where you do the most critical part right away, but you handle all the other side effects in the background, where things like safe retries are way easier to manage.
And really, that brings us to the ultimate takeaway here. In these big distributed systems, failure isn't just a possibility, it's an absolute certainty. So the real question you have to ask isn't if your system will fail, but how it will fail. And having tools and principles like idempotency is what ensures that when it inevitably does, it can recover gracefully without ever charging you twice.